Hey, everybody. So, here we go. We are shifting gears, and in fact, we're going to shift our XY coordinate plane in just a moment. But right now, what I need you to do is to find a straight edge of some type in your house, ruler, edge of a book, something that you can draw a nice straight line with. I would like you to be careful with your notes today. Up at the top of a nice clean sheet of paper, I'd like you to write down inclined planes or incline plane problems. So here's what I need you to do. With that straight edge, can you draw a right triangle in the middle of your paper? I need you to draw big enough that we can draw many different vectors on it. Okay? So if you could, go ahead and take a moment and draw in a large right triangle. On that triangle, I'm going to place a mass, M, in the middle, and I'm going to label the angle, theta, down below. All right. So my question has got to be two things. How does the angle of the incline affect the acceleration? I feel like you could answer this long before physics. The steeper the angle, what's going to happen? But then number two is how can we quantify that acceleration? And that is where it gets interesting. But before we do that, let's go to a quick clip where we take a look at a mass going down an incline. To take a look at incline planes, I want you to grab a textbook. If you don't have your physics textbook handy, grab something else. Then, can you find a ball or some object? It could be a coin if that's what you have. Anything. Something in your pocket, and place it on the book. Now, right now, I see two forces acting on this ball. Yeah, that's right, good. Gravity is straight down, mg, and what force is pushing it back up? Yeah, the normal force. Which one of those is bigger? Yeah, right now, they are the same. Good. Now, the word normal force means perpendicular to the surface. So let's think about what that means when my surface changes direction. Now, my surface is inclined, or it is an inclined plane set at an angle. That angle that we would measure would be from here down to the horizontal. This would be our angle theta. Here's our object. And which way is gravity acting on it? No. Gravity, oh wait, did you say gravity is still acting straight down because gravity is a force between the ball and the earth? Oh, then you were right. Nice, that's good. Phew. But what about the normal force? Point. Which direction is the normal force acting? Oh, the word normal means perpendicular to the surface, you say? That's right. So that force is actually acting perpendicularly. So now, the force of gravity and the normal force cannot be equal, right? So how do we go about that? Well, what we are going to do is to take our gravity vector, mg, and break it up into components. All right. Now, what happens to the acceleration as the angle gets greater? You don't need a demo to see this. You should just know it. But if I have a certain angle, theta, that angle gets greater and greater, I think that you can see that it goes faster and faster until when that angle is equal to 90 degrees, what should the acceleration be? Yeah, that's right, gravity. Was that necessary? No. Pretty sure you could have seen that anyways. Well, there you go. Okay, so now that we've taken the time to watch a ball roll down an inclined plane, how do we quantify it? Well, let's take a look at the vectors. If you would, please, and I hope you drew your triangle big. If you didn't, go back and draw big. I'm going to draw my free body diagram right on this triangle. And the first force that I'm going to draw is the force of gravity. Now that force always, and I hate the word always in physics, but it always acts straight down. So I'm going to draw that vector, and you can see in my example, I drew it to the bottom of the triangle. although that's just for aesthetic purposes at the moment. And I'm going to label that vector mg. Now, the other vector that I would clearly draw would be the one that was labeled the normal force, Fn. But what does the word normal mean? Perpendicular to the surface. So the normal force is instead going to be drawn, see if I can do this faster, perpendicular to the surface. I guess I'll just do it with my free hand. Now, take a look at those two vectors. Are they in the xy coordinate plane? Well, I guess technically they are, but one of them is definitely at an angle in the xy coordinate plane. Now, this mass is going to go down the incline. I am going to make down the incline the positive direction. The other direction, my y direction, I'm going to make perpendicular to the surface. So those are my two directions, blah, blah, blah. Now, this vector I need to label as the normal force. So how do I sum up the forces when mg is clearly at an angle? What did I do with motion when we took an object and we fired it off at an angle and we had to separate it into its x and y directions? Yeah, that's right. We had to break it up into components. So my first component is going to be a vector that is perpendicular to the surface, so it's in the same direction as that positive arrow, the same plane. And it's going to end here. It's going to end such that it forms a right angle with the other component that is then parallel to the surface. Just this once, I'm going to label this the force parallel and the force perpendicular. Now, here's where it gets interesting. We can play the game of if this angle is that angle, then that angle is this, and if this angle is that, then that angle is something or other. You ready? Don't you remember that game from geometry? Teacher would stand up at the board, and you'd say, "Yep, I got it." And actually, most of you did, because you're the smart ones. But maybe I wasn't. So let's take a look. What angle do I have here? Because what I want to be able to do is to solve for the F parallel and the F perpendicular with respect to the angle of the incline and that weight mg. So if this is my angle theta, and mg by definition always acts straight down, then that is going to be a right angle. If that's going to be a right angle, I'm going to let this angle be phi. It's just another Greek letter. Relax. Now, if that angle is theta, I'm sorry. Relax, that angle is just phi. It's just another Greek letter. But if that angle is phi, then this angle, where the question mark is, actually is going to be theta. Because theta plus phi should be equal to 90 degrees. All right, take two on showing that that angle is theta. I wasn't going to do this, but then I was just watching my video and man, it doesn't need to be that hard. Here we go. Now, what I did was I redrew a triangle. Notice the angle is a little different, but that's okay. We're still going to call the angle theta. This time, when I drew the mass, instead of drawing it as a box and drawing the forces from the center of the box, which is proper physics technique, I'm instead going to let it be a point mass. That way I can just represent it as a big dot. Now, when I do that and I draw in my vectors, the angle thing becomes much more clear. We're going to have mg acting straight down, and we're going to have the normal force perpendicular to the surface. Now, when I break that up into components, I'm going to have And this would be my force perpendicular to the surface and the force parallel. But what are the angles involved? Well, if this angle is theta, the angle of the inclined plane, and this is a right angle because gravity is always straight down. So if it's straight down and it hits a horizontal, then it's 90 degrees. I'm going to let this angle up above in my triangle be 90 minus theta. Oh, that was so much easier. Now, if that angle is 90 minus theta, take a look at the force perpendicular vector. That force perpendicular vector is clearly 90 degrees from the surface because it's perpendicular, like that's what it's called. So if that's 90 minus theta, this angle right here, then our angle that we're looking for right there is going to be theta. So if this angle is theta, I'm going to ask for now, just trust me. That angle is theta. Then mg is the hypotenuse of this triangle. That means that F parallel is opposite. This force is opposite the angle. So if I were to solve for F parallel, it's parallel to the direction of motion. To solve for that, it would be the sine of theta equals F parallel over mg, because sine is opposite over the hypotenuse, and the hypotenuse of this triangle is mg. So this force parallel becomes, actually maybe I'll show it here. It becomes mg sine of theta equals force parallel. To find the force perpendicular, I bet you already see where this is going. Because it is adjacent to the angle, I can use the cosine of theta equals F perpendicular over mg, or it's going to be equal to mg cosine of theta equals F perpendicular. So what I've just done is I have taken the vector mg and I've broken it up into its components, where F parallel is going to be mg sine of theta, and F perpendicular is going to be mg cosine of theta. Now, what I've essentially done is I have replaced that mg vector with those two components. Now, I draw them very carefully as dashed lines to indicate that they are components and not the vectors themselves. I also am really careful that my x and y, or my perpendicular and parallel vectors, are 90 degrees to each other. So what the heck does this have to do with what we're doing? Oh yeah, if I want to find the acceleration, because the question is, how can we quantify the acceleration? You knew this was coming. The sum of the forces is going to cause the mass to accelerate. And I'm going to look at the sum of the forces in the x direction. But look, the direction of our x direction has changed, where x is now down the incline and y is perpendicular to it. So if I made down the incline positive, then the only force that is acting in that direction is going to be a positive mg sine of theta. That is going to cause the mass to accelerate. Yep. And in fact, what we see happen is that the masses cancel out, and we are left with that the acceleration is equal to g times the sine of theta. Now, the sine of theta is always less than 1, less than or equal to 1. So the acceleration on an incline is always going to be less then 9.8. Oh, unless the angle is 90 degrees, then it is 9.8. And then that's what we saw, it just falls. Okay. Now, Galileo actually did this experiment to demonstrate that falling bodies accelerate at the same rate independent of their mass. He didn't drop masses from the Leaning Tower of Pisa like the story says. What he actually did was he ran a series of experiments and changed the incline angle and showed that once that angle got to 90 degrees, that the acceleration would be 9.8 and that the mass didn't affect the results. Brilliant. Now, right now you're probably thinking, oh my God, this is taking so long. That's what I'm thinking, making this video. Is this all there is to it? Of course not. Take your paper, flip it over. Take a look at another example.